Hello everyone. In this session, we are going to think about transistor common base characteristics. At the end of this session, students will be able to describe transistor common base voltage current, that is VI characteristics. So these are the contents of this session. Now let us go for the introduction to circuit configuration. Common base in the sense, the bipolar junction transistor, that is BJT, it consists of three doped regions. These three doped regions are emitter region, base region and collector region. So with the three terminals, external terminals, emitter, base and collector. So transistor can be connected and operated in one of the three different circuit configurations, like common base circuit configuration, common emitter circuit configuration and common collector circuit configuration. So in this session, we are going for the response of a transistor for the variation of current and voltage. For the variation of current and voltage at the input and output side of a transistor connected in common base circuit configuration. Now let us first think about what is the common base circuit configuration. Let us go for the circuit diagram in which the transistor is connected in common base circuit configuration. Now this figure shows the circuit diagram for the transistor connected in common base circuit configuration. And we are going to obtain the characteristic, that is the voltage current characteristic of transistor in common base circuit configuration. So in this common base circuit configuration, now consider the NPN transistor. In this, in addition to the biasing DC voltages, to bias emitter base junction, the external DC voltage VEE is connected. Since transistor is NPN, emitter is of N type, base is P type and collector is again N type. So negative terminal of VEE is connected to emitter and positive terminal of external DC voltage VEE is connected to base. Whereas one more DC voltage VCC, that is used to reverse bias collector base junction. Normally emitter base junction is forward biased and collector base junction is reverse biased. So positive of VCC DC voltage is connected to collector, N-type collector, and negative of DC voltage VCC is connected to base terminal. So in addition to this biasing of emitter base junction and collector base junction, using two DC voltages, the input AC signal, the small amplitude input AC signal, that is to be amplified. Is applied to the emitter of transistor with respect to base. So the input current, that is caused due to input AC voltage signal. So that is input current is emitter current I flowing in the emitter terminal of a transistor. And input voltage is a voltage at emitter with respect to base, that is voltage VEB is the input voltage and the current I is the input current, that is the emitter current. Whereas the current flowing in the collector terminal, that is the collector current IC, and the output voltage, that is the voltage taken at collector with respect to base, that is designated as VCB. So output signal, the amplified output signal is taken from collector with respect to base. So in this way, the input is applied to emitter with respect to base and output is taken from collector with respect to base. So base terminal is common to both input and the output side of transistor amplifier connected in common base circuit configuration. So that's why this circuit configuration is called as a common base circuit configuration. Now let us go for the characteristic of transistor connected in common base circuit configuration. It is a response of transistor for a variation of input current and input voltage for a given value of output voltage. So we are going to think about characteristics, that is the voltage current characteristic of transistor in two parts. One is the input characteristics, another is output characteristics. So this figure shows the typical voltage current characteristic. Voltage current characteristic of a transistor connected in common base circuit configuration. So input characteristic, what is the input characteristics of a transistor in common base circuit configuration? So input characteristic of transistor in common base circuit configuration, it is a graph of input current I, emitter current I versus the input voltage, that is the emitter to base voltage VEB. For given certain constant value of output voltage, that is the voltage at collector with respect to base VCB. So it is a plot of I versus VEB at certain constant value of collector to base voltage. Now this graph shows there are three characteristic curves, current voltage curves for three different values of constant values of output collector to base voltage, for different values of collector to base voltage. So from this voltage current characteristics, that is the input characteristics, it is seen that as emitter to base voltage, that is the input voltage, emitter to base voltage is increased from zero value initially, as long as emitter to base voltage is below the cut-in voltage, is less than the cut-in voltage of a transistor or a knee voltage of transistor. The current flowing in the emitter terminal is very small. It is practically assumed to be zero, very small. The emitter current is zero. When after cut-in voltage, when emitter to base voltage just exceeds the cut-in voltage of a transistor, that is base emitter junction cut-in voltage of transistor, the emitter current I increases very sharply, rapidly, with further increase in emitter to base voltage, So for small change in emitter to base voltage, there is a large increase in emitter current I. So this indicates that the input resistance of transistor in common base circuit configuration is very small, very low, because emitter current, that is generally in terms of milliampere, it is very large. For small change in emitter to base voltage, there is large change in increase in emitter current. So the input resistance of a transistor in common base circuit configuration is very small. So that is given by the dynamic input resistance of a transistor in common base circuit configuration, Rin, is equal to delta VEB, change in emitter to base voltage, divided by change in emitter current at certain constant value of collector to base voltage. From three different graphs, as VCB, collector base voltage, that is the reverse voltage, is increased. As collector to base voltage, that is the reverse voltage, increases, there is slight increase in the emitter current I. There is slight increase in emitter current I for given value of emitter to base voltage, So that is due to the early effect. Now let us go for the output characteristic of a transistor in common base circuit configuration. So the figure shows a set of graphs for output collector current versus output collector to base voltage VCB. So it is a plot of IC versus VCB at certain constant value of input emitter current I. So output characteristics can be divided in three different regions: saturation region, active region, and a cutoff region. So in active region, both base emitter junction is forward biased and collector base junction remains reverse biased as usual, and collector current IC depends upon the value of input emitter current I. So collector current IC is directly proportional to input emitter current I. As emitter current is increased or decreased, corresponding to that, collector current increases or decreases. So emitter based junction remains forward biased and collector based junction remains reverse biased. The operation of transistor is linear, and collector current is approximately equal to the emitter current, because collector current is slightly less than emitter current by the value of a base current. So the transistor can be used as a constant current source by operating the transistor in its operating active region. In saturation region, the output collector current IC rises to certain maximum possible value or saturation value for a given value of input emitter current I. So in the saturation region, collector to base voltage, when collector to base voltage is reduced about 0 volt, closer to 0 volt, so the collector base junction is remains forward biased, as well as emitter base junction, which is already forward biased. So both the junctions of transistor remains forward biased, and the voltage drop across collector base junction is minimum, and IC rises to maximum possible value, saturation value, for the given value of input emitter current I. In the cutoff region, the region below the I equal to 0 ampere curve, that is the cutoff region of a transistor. So in this region, both the junctions of transistor remains reverse biased. Transistor does not conduct, it remains in a off state. In active region, IC slightly increases with a large increase in VCB, so that is due to early effect. As collector to base voltage is increased, there is slight increase in collector current. So this indicates that the dynamic output resistance, that is AC resistance of transistor in common base circuit configuration, RO, is given by delta VCB divided by delta IC at certain constant value of input emitter current I. Since there is slight increase in collector current for a large change in or increase in collector to base voltage, so output resistance of transistor is very large, very high in common base circuit configuration. The current gain of transistor is defined as alpha, designated as alpha. It is the ratio of output collector current IC to the input emitter current I. Since IC is slightly less than I, the value of alpha, that is current gain, is less than 1 for a transistor in common base circuit configuration. So transistor does not provide any current gain in a common base circuit configuration. As far as voltage gain of transistor is concerned, the voltage gain of transistor is equal to the ratio of output voltage VCB to the input voltage VEB. So transistor provides a voltage gain for the input signal, because VCB is larger than, very much larger than the input voltage VEB. The student can pause video here and think over this question and try to answer this question. What is the cut-in voltage of a transistor? The answer is the minimum voltage required to be applied between base emitter junction of a transistor to overcome the barrier potential. To overcome the barrier potential and start current conduction. To cancel out the barrier potential and start current conduction across base emitter junction, and thereby the emitter current flows, and from emitter current, collector current as well as base current flows. So this is the reference. Thank you.